Hello, I'm Katie Steckles.
And I'm Peter Rowlett. Katie, what's today's mathematical object?
It is a Möbius band.
Okay.
And this is, I feel like, almost a cliche in terms of objects that people associate with maths. This is maybe a slightly minor bee in my bonnet that I have about this, because I have studied topology and I know a lot of things about the Möbius band. And the problem I have with it is that a lot of people show the Möbius band to people and say, this is a Möbius band, look what happens when you cut it in half. Mm-hmm. So for anyone who hasn't seen a Möbius band before, the idea is that you take a strip of paper, you stick the ends together, but before you stick them together, you put a twist in it. So, you bring them together as though you were going to make a kind of a loop, and then you turn one side over and stick it down. And if you've done that, you get something which does something slightly weird and interesting if you cut it in half down the middle. And a lot of people do that, and they go, oh yeah, that was fun. And then they never talk about it again. And I find this really upsetting, because it's one of the most fantastic puzzles in maths to answer the question, why does it do that? What's going on here? What is this shape, and why does it behave like this?
Yeah, I was sort of thinking when you said Möbius band, like, what do I know? I know that it's like a cylinder, but you put a funny twist in it, makes an uncomfortable armband, and if you cut it in half, then weird magic happens. That's about it.
Yeah. And that's, for a lot of people, that's the extent to which they interact with it. And it's frustrating, because I really love showing it to people, but I always take about 20 minutes because there's so much to say about it. And I guess, so the way that I would always introduce the idea is I'd get people to make one, because obviously it's much more interesting if you've seen it in your own hands and you've seen it happen yourself. So if you're listening along and you would like to do this, you can join in. So pause the recording, go and get a bit of paper and some sellotape and stick it into a Möbius band. And
if you're going to do that, you want a sort of thinnish piece, so cut a strip of paper.
Yeah, I usually say cut the margin off a piece of A4.
Right.
Is it roughly the right amount of paper? And the first thing that I suggest people do is get some kind of marker pen and draw a line down the middle of the Möbius band. Before you even go near a pair of scissors, get a pen and draw a line down the middle, because if you do that, you start drawing a line and you keep going round, and eventually you get back to where you started drawing, but you find that you're on the back. And this kind of makes sense, because you started off with a piece of paper that's got two sides. It's got a front and a back. And when you put a twist in it, you join the front onto the back and the back onto the front. So what you've got now is a shape with one side. So if you draw a line along it, you'll come back to the position where you started drawing, but you'll be on the other side of the paper. And you can, in theory, just keep going and go all the way around again, but you'll go around the whole thing twice before you get back to the actual point where you started. And I guess this illustrates that the Möbius band has only got one side.
Yeah.
Which is the origin of the hilarious topology joke, why did the chicken cross the Möbius band? There is no punchline. You can just shrug. There are many options. But it's a great joke. And so that's one thing. And people sort of, when you realise that this is a shape with one side, that kind of puts it into a slightly weirder category, because you're used to shapes, especially shapes made out of paper, having two distinct sides. But one of the things about a Möbius band, in fact, one of the things that topologists like to do in terms of how you think about shapes, is to imagine a tiny ant standing on the surface. Which is kind of a metaphor for considering a shape's local properties as opposed to global properties. But, it's always an ant standing on the surface, because ants are small. And if there was an ant standing on a Möbius band, it could walk around the whole thing, and it could walk to any point on the surface without having to climb over the edge. And I think there's a famous MC Escher print that's got two gigantic ants walking around a Möbius strip. So that's maybe a nod to that, I don't know. So that's the first thing. And then and only then would I permit people to get a pair of scissors and carefully cut along that line that they've just drawn, especially since they've now got a line to follow, so it makes it a lot easier. And if you do this, it's especially weird, because if I just had a cylinder and I drew a line down the middle, I'd obviously have to take my pen off and draw a second line around the inside if I wanted a line on both sides. But if I cut that in half, it would come apart into two narrower cylinders. And that's a very sort of intuitive thing that would happen.
Sort of top half of the cylinder and the bottom half of the cylinder you've separated.
Yeah, I guess. Yeah. But the thing about a Möbius band is that I started off with a strip of paper with, I guess, a left-hand edge and a right-hand edge. If you imagine I'd taken the strip of paper and dipped one edge in red paint and then turned it over and dipped the other edge in blue paint, and I had a single sort of stripe of colour down each edge. I've put the twist in and I've joined the red edge onto the blue edge and the blue edge onto the red edge. So what I've actually got is a shape with one edge. And if I cut that in half, it's not going to come apart into two pieces because there's only one edge. And I've kind of cut down the middle and unzipped the whole thing. And in fact, you can do things with zips. You can attach zips together funny and end up with a thing that unzips like a Möbius band and doesn't come apart into two separate pieces. And it's a really fascinating thing to do. And I've done it hundreds and hundreds of times. And every time I do this and cut a Möbius band in half, I'm still slightly weirded out by it because it's not what a thing should do. But it's just a function of the fact that this is a one-edged shape. And a complete Möbius band, you could run your finger all the way along the edge and it would go around the whole thing twice and come back to where you started. You could attach some kind of frill along the edge. It would just be one long piece that wraps around the whole thing twice. Essentially. So these are the kind of standard things that you see people do. And there's lots of other ways you can kind of extend this. So cutting a Möbius band into thirds is quite fun. Like for anyone who's listening along at home and has already got surrounded by strips of paper and tape and scissors and everything, cutting it into thirds. So you start a third of the way in from one edge and just keep going and see what happens. You could put more twists in it. So a Möbius band with two twists. Which is incidentally the thing that you get if you cut in half a normal Möbius band with one twist. So you put two twists in it, cut that in half, something interesting happens. 3 twists is very interesting. So 3 twists in a Möbius band. You might need a longer strip of paper for that because it gets quite twisty. But if you cut a 3-twist Möbius band in half, that is incredible. And it's a fun thing to play with. And you can sort of see patterns in what happens and, how many bits do you get and what happens to the bits and that kind of thing. But all of it can sort of be explained by thinking about what you fundamentally got there as a shape. So if you put one twist in a Möbius band, you join one edge onto the other edge. If you put 2 twists, you join the edges back onto their original edges again. So you've got 2 edges. So if I cut a 2-twist Möbius band in half, I would expect to get 2 pieces. And this is the kind of thing that topologists do. They kind of, they can make predictions about how things are going to behave based on their properties. Yeah. One other thing about the Möbius band that topologists are particularly obsessed with is that it's what's called a non-orientable shape. And this is a property which means that you can't set up coordinates on the surface of a Möbius band. And the reason for this, if you kind of imagine drawing a little pair of XY axes somewhere on the Möbius band. So you get a pencil, draw a pair of XY axes. And I'm kind of visualising this by having 2 of my fingers at right angles to each other in the shape of a letter L. So that's somewhere on the surface of a Möbius band. But of course, if my XY axes are there, I could just move them along a bit. I can move them to the right and I'd still have X pointing up and Y pointing to the right, or whichever way around they are. It's X to the right, isn't it? It's conventional, but yeah. So if I do that and I keep going all the way along the Möbius band, eventually I'll get back to where I was, but my axes will be upside down because I've gone through a twist, right? So if I try and define a set of coordinates on this Möbius band, it can't continuously exist all over the whole surface because it will get mixed up and wrong at some point, which essentially is why it's non-orientable. You can't decide which way is up on a Möbius band because if you just go for a walk and come back, it's suddenly down. Right. Which is quite a nice sort of conceptual property, but it means that a Möbius band or anything that I guess contains a Möbius band has this non-orientable property, which is quite nice.
So it's sort of if you're the ant stood on the Möbius band, there's an edge to your right, but that's also the same as the edge to your left, and that's kind of the problem. And if you go far enough, they swap round. Yeah,
basically.
Very weird.
Because defining the coordinate system on something needs to not be dependent on where you are. Essentially, it needs to be consistent across the whole thing. So, it's because another way to think about a Möbius band. So, I guess the term would be a fibre bundle. And whenever I try to picture a fibre bundle, I always think of a hairbrush because that's the way it was first defined to me. But the idea of having a thing with a thing sticking off it at every point. Right, so like a comb or a hairbrush, like a comb would be a one-dimensional line with like teeth sticking off it, or a hairbrush would be like a flat shape with things sticking off it. And in the same way, you can think of a Möbius band as being a circle with a bit of line or a line interval attached at every point on the Möbius band. Okay, so in the same way that a cylinder is a circle with a straight line attached at every point, and all of those straight lines sit next to each other like teeth on a comb, going all the way around the circle. I'm trying to think if there's a good sort of physical analogy for this, but you've got a piece of string and you attach a vertical stick in the middle of the stick to the string at every point, and they will all kind of sit upright, and you can join the ends of the string together and you get this cylinder shape. And the Möbius band is just that, but with a twist. So at some point you've broken the string, turned one of the strips of wood upside down, and stuck them back together with this twist, which means you've still got a circle and you've still got a straight line attached at every point. And that in some sense means that the cylinder and the Möbius band are the same, right? Because one of the things about topology is that you can stretch and squash things, right? So if you retract each of those lines, if you make them all shorter and shorter and shorter, you get a thinner and thinner cylinder, and eventually you'll get a circle. Yeah. And if you do the same thing with the Möbius band, you'll still get a circle. So in that sense, they're the same as each other because they've got the same sort of structure, but they are very, very different because of this twist. So I don't know if that helps to sort of picture what's going on with the Möbius band, that it's kind of made up of infinitely many line segments squished together or something like that. And the other nice thing that you can think about, if you're thinking about like more and more twists or different combinations of Möbius bands, if you picture the boundary of a Möbius band, so for a regular one twist Möbius band, the boundary of it is just a circle, because you've got this single line that goes round. The boundary of a two twist Möbius band is two circles because it's got two different edges, but those circles are linked together. So if you're thinking about knot theory, or links, I guess, a branch of knot theory, the boundaries of ribbons, I guess is the technical maths term, are often like Möbius type shapes, I guess. So you take a ribbon, the boundary of that is a knot or a link in knot theory. So that's also quite a nice sort of connection.
So I think the thing that slightly weirds me out about the Möbius band is it's one of these things where you can describe it as a very complicated mathematical thing, and you think, oh, well, that's fine. That obviously lives in some fairly complicated mathematical space that I can't possibly access, but I can try and visualize it or whatever. Whereas, in fact, it's something you can make just by twisting a bit of paper over. And it's kind of weird, that. And although it seems every day because you see it a lot in pop math stuff, but actually there's some real weirdness going on at the heart of it.
Yeah, well, this is what I object to, is people playing with Möbius bands, but without being quite seriously freaked out. Like if you've not thought about it long enough, I think what I want people to do is understand why it does what it does. Which, once you think about like how many edges does this shape have, or what's the structure of this shape, it kind of explains that kind of thing for you. So, I'd rather people come out of it with that kind of understanding rather than just going, "That was weird."
Yeah, definitely. And so because this is a real object that exists in the real world, does that mean that it has applications?
Absolutely. It definitely has lots of very, very important applications that definitely are used all the time. So the classic one, I think there was a historical patent application for a Möbius drive belt, which it turns out is quite often a thing that people use. So this idea that if you're going to attach a drive belt around two wheels, if you put a twist in the drive belt somewhere, it will wear the belt evenly on both sides, which is quite an interesting thought, and I guess in theory would make it last the same amount of time because it's got a finite thickness. I don't know. Like if it wears through from one side, it's the same if it wears through from both sides equally. But I don't know. Maybe there are some kind of engineering applications for this. I think also the fact that it's got a twist in it means that there's more kind of stress on the whole system, which makes it last less long. Or it's not an easy thing. Like as you mentioned earlier, it makes an uncomfortable bracelet. So as a Möbius nerd, I often, when I get given a wristband, especially for a science festival, I always say to the person putting it on, "Oh, could you just put a twist in it?" And they're like, "Why would you do that?" And then I spend the whole day or week with like a bit of plastic digging into my arm in an uncomfortable way for maths. So it's worth it. But yeah, one of my actual favourite real world applications, you can't see me doing finger quotes, but one of my favourite applications of the Möbius band is the Möbius roller coaster. And this is incredible. So if you imagine It's essentially a double roller coaster. My slight playing too much Roller Coaster Tycoon is going to become apparent here now. But it's a double track roller coaster, and it's got two trains that set off from the station at the same time. And I think there are some of these in the real world, like I can't remember where one of them is, but if you search for Möbius roller coaster, there are actually photographs of real roller coasters that have this setup. But essentially, one of the tracks immediately drops down, and the other one carries on level, and the one that's dropped down goes underneath the other one. So the tracks have essentially swapped over, and then the two roller coasters go around and do whatever they're going to do, you know, all the different parts of the roller coaster. But then when they come back into the station, the trains are on the other tracks. So they're on opposite sides. So you get on the roller coaster, and your friend gets on the other train of the same roller coaster, and you're like, oh, we're going on a roller coaster together, I'll see you in a bit. And you come back and you look to your right, and your friend is actually to your left now, which I imagine is kind of a fun thing. But because of this sort of property, you can do that. And what it essentially means is that this roller coaster only has one track, but it goes through the station twice on its route. Which is it's kind of nice, sort of making use of this principle to do something slightly fun. And I guess it means that the trains swap which route they're going to do each time. So if you wanted to ride the whole roller coaster, you don't even have to get off. You just wait and go around it twice, and you'll get a different riding experience each time.
Cool. If you want to get in touch, we're both on Twitter. I'm at Peter Rowlett.
And I'm at Steckles, and the podcast itself is at Maths Objects.
We both blog at a website called aperiodical.com, and if you go there, you can get more episodes of this podcast.
And if you have any suggestions for other objects that we should podcast about, or if you've made anything incredible using scissors, paper and tape that you would like to share with us, please drop us an email, objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.